All right. Well, officially, good afternoon, everybody. Welcome back to our last day of Intro to Physics of summer 2022. This is day 23. We have made it this far. Wow. Awesome. So, like I said yesterday, I'm going to post on Canvas a kind of course overview with summary slides for each chapter, including some of the chapters that we didn't get a chance to cover together, like rotational motion, that sort of thing. So that you have those as kind of a little cheat sheet of sorts with definitions and equations and variables and helpful things like that. So make sure you check Canvas for that. Make sure that you download any of the course information, course materials that you want to have access to later on, because you will probably lose access to this class in the next few days. So without further ado, let's continue on with gravity. Okay, so yesterday we talked about like how we came to our understanding of what the universe looks like. We talked about Newton's law of universal gravitation and some sort of the similarities and differences between our force of gravity equation that we had been using previously, F equals mg. And now we introduce this idea of the universal gravitational constant, capital G, and how the distance between the centers of the objects matters. And so now we want to think about how we can use that equation in different scenarios. For example, finding the mass of the Earth. So it's not exactly like we can take the Earth and put it on a scale and figure out the mass that way, like we can with other objects that are on Earth. It's sort of difficult to do that in space with planets. So the question, how can we find the mass of the Earth, was sort of a puzzling question. But we have a great advantage with the moon. The fact that we have the moon orbiting around us, using that force of gravity equation can give us information about the mass of the Earth. And this is also how we can use satellites or moons around other planets to find the mass of that particular planet and the mass of those moons or satellites. Same sort of situation. So observationally, we know that the moon's orbital period is about 27 days, and its orbital or angular velocity we can calculate in this way. So we know a complete circle or a complete orbit is 2 pi radians. And if it covers 2 pi radians in 27.32 days, we can calculate the angular speed from that. So we know 1 day is 24 hours, 1 hour is 60 minutes, and 1 minute is 60 seconds. And so that gives us an orbital velocity of 2.66 times 10 to the negative 6 radians per second. Remember, the variable for angular velocity or orbital velocity in this case is lowercase omega. Now, the distance to the moon is approximately 385,000 kilometers. And that was determined by Aristarchus around 270 BC by using the duration of a lunar eclipse. And then Hipparchus also kind of confirmed that distance about 100 years later using a different method called parallax, which was during a solar eclipse. And so parallax is basically a way we can measure the distances to really far things. So distances to stars, for example. If we compare that star to a farther background star, then we can kind of figure out, the angle that that star moves through in 2 different parts of the Earth's orbit. So for example, if you stick your finger out in front of you like this, and you close one eye and then the other eye, compared to a background object, you can kind of see your finger like jumping back and forth when you close one eye versus when you close the other eye. So if we measure the position of a star against the background stars in the summer, for example, when the Earth is on one part of its orbit, And then we look at that same star in the winter when the Earth is in the other part of its orbit. That's kind of like closing one eye and then the other eye on a more massive scale, on the scale of the Earth's orbit. And so we can see how that star jumps back and forth in relation to those background stars. So if we measure that angle that it jumps through, we can figure out the distance to that star, because there's a relation, the parallax angle, excuse me, is a relation between distance and that angular displacement. So using both of those methods, right, solar eclipses and parallax versus how long a lunar eclipse lasts, they, Aristarchus and Hipparchus, figured out a rough distance to the moon. And they were only off by about 1% in this final calculation. So that's pretty impressive for those methods. Okay, so yesterday we got this equation for the acceleration due to gravity as being G, big G, our universal gravitational constant, times the mass divided by that distance squared. And since that force of gravity pulls inward towards the center of the orbit, it is a centripetal acceleration, which we also said is r, the radius of the circle, times omega squared. Okay. So that means the mass is r cubed times omega squared divided by g. And so the distance, we need to put that in meters as opposed to kilometers. And that's, again, because this constant g has meters built into it as its unit, meters and kilograms. So we need those units to be consistent. Otherwise, we can't use this value of g. We found omega to be this 2.66 times 10 to the negative 6 radians per second. So we square that, divide by g. And we get a mass of 6.05 times 10 to the 24 kilograms. So now the current measurement of the mass of the Earth is 5.97 times 10 to the 24 kilograms. So like I said, it was only off by about 1%, even using these sort of crude observational methods for determining the mass, which I think is pretty impressive. Okay, so here's a question I want you to think about. Just for the sake of time, I'm not going to give you a ton of time to think through this question, just a few seconds to sort of organize your thoughts. So if the gravity outside the Earth looks like a 1 over r squared function, right? We talked about yesterday how it's an inverse square law. Force of gravity equals g times m1 times m2 over r squared. So if that's how the gravity outside of the Earth looks like, right, off the surface of the Earth and beyond, what does the gravity inside the Earth look like? And if we went to the exact center of Earth, like if we could drill a tunnel through the Earth, would you feel an extremely intense gravity due to that inverse square law, right? Because if your r is measured from the center of the Earth and you're at the center of the Earth, does that mean that you feel infinite gravity at the center of the Earth? What does that mean? So take a second and think through this question, come up with a guess, and then we'll talk about it in maybe 10 to 15 seconds. Okay, so 3 different options here, right? Yes, the mass of the Earth doesn't change and r goes to 0, so you would feel an extremely intense gravity. Or no, Earth's gravity now pulls you out, so you get ripped apart. That'd be unfortunate. Or no, Earth's gravity cancels out in different directions and becomes 0. And that one is our correct answer. Earth's gravity cancels out in different directions and becomes 0. So here's a picture of this scenario, right? Let's say we have this tunnel through the center of the earth. Right here's the center, this blue dot, and we're dropping an object through that center of the earth tunnel. So once we're inside of the earth, the mass that we're considering for our force of gravity calculation is only the mass that's inside the radius where the object is located. And so we call this the enclosed mass. So wherever this mass falls, as it falls down, that enclosed mass gets smaller and smaller and smaller. So the mass that's outside of that sphere will kind of factor out of the equation, cancels out. But the mass inside of that sphere, that enclosed mass, is what pulls that object inward towards the center. And so you can see as that object gets closer and closer to the center, that enclosed mass gets less and less and less. So if we were to kind of mathematically think about this, we can calculate the acceleration due to gravity inside the earth and see how that kind of affects things. All right, so there's our equation for the center, for the acceleration due to gravity. G little g equals big G times the mass divided by the radius squared. Okay, so the mass that we're considering now is no longer the total mass of the earth. It's the mass that's enclosed in that radius, however far that ball has fallen. We can know from maybe chemistry that the mass is related to the density of the object and the volume of the object. So mass is density times volume. The volume of a sphere is 4/3 pi r cubed. So if we combine those two equations, that means the mass that we're considering is the density of the earth times 4/3 pi r cubed, and that r is the distance from the center to wherever the ball is at that moment. So the acceleration due to gravity at that random point within the earth is big G times the mass, which is now density times 4/3 pi r cubed, divided by r squared. So that r squared on the bottom will cancel out two of those r cubed on top. So big G times 4/3 rho density pi r is our acceleration due to gravity. The total mass of the earth is 4/3 times the density times pi times our radius to the surface. R0 is like our initial radius cubed. Okay, so we can see here, if we rearrange this equation a little bit, we have these two similar factors, this 4/3 rho density times pi. And so we're left with this fraction that we have to consider, right? The total mass of the earth divided by the radius cubed. So we can plug this into our above equation, right? Because we have that similar factor, 4/3 rho times pi. So if we plug in the mass of the earth over r0 cubed in for that term, we get this result. Little g at that radius, the acceleration due to gravity at some random radius, equals big G times the mass of the earth divided by the radius of the earth cubed times the radius that the ball is currently at. Okay. So doing a little bit of rearranging here, if we take one of these r0 terms and just kind of pull it to the side of the fraction, we end up with this ratio, the radius over, the random radius that we're at over the radius of the earth. Okay, and we know the gravity at the surface is big G times the mass of the earth divided by the radius of the earth squared. And you can see we have that term right there in that equation. So we can even further simplify this equation to say the acceleration due to gravity at whatever location the ball is located at is the surface gravity times that random radius divided by the radius of the Earth. Okay, so this means that the gravity will increase as you get farther from the core. So as we go farther away from the center of the Earth, gravity increases proportionally to that radius, right? So as the radius of the ball, let's say we're starting the ball at the center and it's shooting out. As that ball moves away from the center of the Earth, that random radius that it's at is increasing. And so the acceleration due to gravity is increasing proportionally to that. The force of gravity is increasing proportionally to g, because remember, force of gravity is mass times g, little g. So as we move that ball farther away from the center, gravity increases proportionally until we get to the surface. Once we get to the surface, we saw yesterday that force of gravity decreases proportional to 1 over r squared. So we have a linear relationship between the distance away from the center and the force of gravity when we're inside the Earth. And then when we move past the surface of the Earth, now we're at a inverse square relationship outside of the Earth. Okay, we're not adding any more mass as we move away from the surface. So gravity is decreasing.
There's some more.
Yes.
I'm having a little bit of trouble following along about this.
Okay, at what point?
The concept. I got a little bit lost, and yeah.
Okay, can you be any more specific about like how I can help explain it? Like what point do I need to explain from?
Uh,
Or is it just like this whole idea is kind of weird to think about?
It's not weird. It's just hard because of the math, and I didn't get it with the math, and the idea is really confusing.
Okay. Yeah, so basically what we're trying to figure out is how the force of gravity changes inside the Earth. Because yesterday we talked about how it changes when we're outside of the Earth and moving away from the Earth. And we said it's an inverse square law. But inside the Earth, as we move towards the center of the Earth or away from the center of the Earth, the mass of the Earth that we're considering is changing. Right, so when we're at the surface and moving away from the surface of the Earth, like going out into space, the mass of the Earth is not changing. We're still considering all of the mass of the Earth in our equation. But inside of the Earth, the only part of the Earth that we're considering is the mass that's within our location. So if I go back to this picture, right? As this ball is changing its height within the Earth, we only think about the mass of the Earth that's contained within that height of the ball. And so we need to have a way to figure out how much mass is contained within this sphere, right? This imaginary sphere. And so that's where this math came in, right? The mass that's contained within that imaginary sphere, that's the height of the ball as it's moving through the Earth, is related to the density of the Earth and the volume of the Earth. Okay, so that's where these equations came in. This is the volume of a sphere, right? So we plug that in there. And then we substituted that mass in here in this equation for acceleration due to gravity that we saw yesterday, right? So That's where this equation came in, and then we simplified because there's r squared on bottom and r cubed on top. So we simplified, canceled out some of those r's. Okay, so this portion is just the total mass of the Earth and the entire radius of the Earth, right? Just so we have something to compare to. So the mass of the Earth considers the entire radius of the Earth. And we saw there that we had those common terms in those equations. So this equation GR, remember, was the acceleration due to gravity at whatever location the ball is at. And here we're talking about the entire Earth, but in either case, we have 4/3 times the density times pi. And those are all constants, right? Those are the same constants in either case. Okay, so we took this relationship then and plugged it into this equation instead of this yellow circle to get this. And then we just rearranged a little bit to get to this step, right? We took one of these r0 cubes, we pulled it outside of the fraction. So we got r0 squared times r0. We remembered that the acceleration due to gravity at the surface right here is g times the mass of the Earth divided by the radius of the Earth squared. So that's that equation. And now that we know that, and we see these similar terms in both equations, now we can relate the acceleration due to gravity at any radius inside the Earth to the acceleration due to gravity at the surface. And we saw that they are different by this factor of the radius of the ball, well, whatever radius the ball is at, divided by the radius of the Earth. So yeah, it is a lot of math, a lot of kind of substituting things into equations and simplifying as best we can to figure out that inside the Earth, the acceleration due to gravity changes linearly with respect to the distance away from the center of the Earth, this term r, right? Whereas at the surface of the Earth here, it changes with respect to 1/r squared. So we have these two different relationships that we're considering. One when we're inside the Earth, and one when we're at the surface and beyond, outside the Earth. Okay, so the acceleration due to gravity and the force of gravity, we have to treat differently if we're talking about something that's inside the Earth versus something that is outside of the Earth. That's basically the point here.
I'm still having trouble like getting it's a lot of stuff that's being thrown at me.
It is a lot. However, this sort of problem is not uncommon in what you'll see in Physics 1, where you have to kind of take several ideas and combine them together and simplify an equation and come up with a relationship. So this is a skill that you should practice. Yes. So this would be like a test type problem, maybe not a homework type problem, but more like a test type problem. Yeah, so my recommendation to you, just for the sake of time, I don't want to kind of talk through this slide again right now. But if you still have questions about it, I can talk to you about it at the end of class, just because we have a lot of stuff still to cover today.
Okay.
Okay. We'll put a pin in it. Okay. So here's basically a graph of what we just talked about, how inside the Earth, this capital R is the radius of the Earth. So whenever we're inside the radius of the Earth, anywhere within the Earth, the force of gravity and the acceleration due to gravity, lowercase g, follows this linear relationship. So the gravity is increasing from the center of the earth outward because we're considering more mass. And then once we reach the surface of the earth, it drops off, it decreases according to an inverse square law. Okay, so this is the portion of the graph that we saw yesterday. This is the portion of the graph that we are adding in today. Okay. So moving on a little bit from this potentially tricky problem. If we have multiple objects that are causing a gravitational attraction on some smaller object, we can combine these gravitational forces using vectors. Okay, so if each of two masses exerts a force on a third, so let's say we're talking about the sun, the moon, and the earth, right? Three objects in space, and the sun and the earth are both pulling on the moon in some way, then the total force of gravity on the moon would be the vector sum of the force of gravity from the earth and the force of gravity from the sun. So this sort of idea where we have multiple objects, more than two objects that we're considering, is called the superposition of forces. We're considering multiple forces of gravity acting on the same object. So here's an example of this. If we have a triple star system. So the research that I had been doing in grad school was with a professor who did research on binary star systems, right? Two stars orbiting around each other, or even more stars orbiting around each other. So here's a triple star system, three stars kind of all orbiting around. So many of the stars that you see in the sky are actually part of binary systems or multiple systems, two or more stars held together by their mutual gravitational attraction. So they're kind of orbiting around each other. So let's say there's a three-star system. At an instant, we're looking at it at an instant when these stars are creating a 45-degree right triangle. So you want to find the magnitude and direction of the total gravitational force exerted on one of the stars, a small star, by the two large ones. Okay, so here's a picture of what I mean. We have these three stars all kind of orbiting around each other. One of the stars is small, and two of the stars are large. Okay, so both this orange star and the red star have the same mass, 8 times 10 to the 30 kilograms. And the smaller star has a mass of 1 times 10 to the 30 kilograms. Okay, and so we just happen to take a picture of it or an observation of this star system when these stars are making a right triangle like this. Okay, so we have a distance between the small star and the red star of 2 times 10 to the 12 meters, and a distance between the orange big star and the red big star is also 2 times 10 to the 12 meters. So we know that this small star is going to experience a force of gravity from this orange star and also from this red star. And so because of that, because of those two forces, this smaller star is going to experience a net gravitational force kind of towards both of them, as opposed to just towards one of them or the other one. So if we want to find the force on this small star due to this orange big star, remember the force of gravity is big G times the mass of one star times the mass of the other star divided by the distance between their centers squared. So F1 here, this first force of gravity between these two stars is big G, 6.67 times 10 to the negative 11, times the mass of the big star, times the mass of the small star divided by the distance squared. Now, we weren't given that distance between these two stars, but since this is a right triangle, we can use the Pythagorean theorem to find it. So remember, the Pythagorean theorem tells us that a squared, this side of the triangle squared, plus b squared, this side of the triangle squared, equals c squared, that hypotenuse squared. And that's the distance that we're interested in finding right now, this c hypotenuse distance. And since it's already squared in our equation, that's why this denominator is just a squared, this first distance squared, plus this second distance squared, because that equals our hypotenuse squared. Okay. So once we do that calculation, we'll find a force of gravity on the small star due to this orange big star is 6.67 times 10 to the 25 newtons. Now we're going to do a similar process of the force on the small star due to this red big star. The only thing that changes here now is that distance between those two stars, right? Because capital G, big G, is always the same, always 6.67 times 10 to the negative 11. The mass of the red star is also 8 times 10 to the 30 kilograms. The mass of the small star is still 1 times 10 to the 30 kilograms. But now the distance between them is given to us as 2 times 10 to the 12 meters. And we need to square that distance in our equation because it's distance squared. So that gives us a force of gravity between those two as 1.33 times 10 to the 26 newtons. So since this small star is slightly closer to this lower red star, it experiences a stronger force of gravity from that star than from the upper orange star. But it still has a considerable force of gravity from that upper orange star. So that's why this kind of darker pink line, F, is a little bit closer to the red star than to the orange star. It's still going to experience a force from that upper orange star, but more so a force from the lower red star, so that that vector is going to be closer to that red star than the orange star. Okay, this is not our final answer yet, though, because we need to find the value of F. But now we have F1 and F2, so we're on our way. So if we want to find the components of these forces, so going way back to like week 1, the components of a vector, the x component of this first force is that force times the cosine of the angle, which we were told in the problem statement is 45 degrees. So the x component of that force then is 4.72 times 10 to the 25 newtons. And the y component would be that force times the sine of our angle. Since it's a 45-degree angle, the cosine of 45 and the sine of 45 are the same value. So we end up with the same value for either component, for both components. Force 2 is only in the x direction. So all of that force of gravity from the red star is pulling horizontally. There is no y component to consider. So remember, when we want to find the magnitude of our, we called it a resultant vector, the result of adding together 2 or more vectors, we can add all of the x components together and then separately add all of the y components together. So that means the x component of our total force is the x component of the first force plus the x component of the second force which gives us a result of 1.81 times 10 to the 26 newtons. And then our y component is the y component of our first force plus the y component of our second force. So 4.72 times 10 to the 25 plus 0 is 4.72 times 10 to the 25 newtons. Okay, so now we have the components of our total gravitational force, but we don't yet have the magnitude and direction. We need one more step in each case to get us there. Okay, so here I rewrote the components. The magnitude of this force, remember this equation comes from the first week of class together when we talked about vectors. The magnitude of the force, we use the Pythagorean theorem to find. So it's the x component squared plus the y component squared. And then we took the square root of that result. So here's our x component squared plus our y component squared. When we square root that result, we get a force, a total gravitational force of 1.87 times 10 to the 26 newtons. And that's our magnitude of the total gravitational force from both of these big stars on that small star. To find the direction, this equation comes from that same PowerPoint on vectors. The direction of the force is the inverse tangent of the y component over the x component. So here's our y component over our x component. We get an angle of 14.6 degrees. So we can see, since we're measuring our angles from that positive x-axis upward or counterclockwise, this little angle here would be 14.6 degrees. And that should make sense if we evaluate our answers here. It should make sense that this is a fairly small angle because we said that since this small star is closer to that red star, the red star's force of gravity is going to be stronger than that big orange star's force of gravity. So that angle of the force will be closer to the red star than to the orange star. Okay, so this would be another type of like test problem, final exam type problem that you might see in Physics 1, just because there are so many different parts to it. And we pulled in information from the first week of class, right? All of this information about vectors and stuff. So whenever we combine multiple topics together, we're talking about a test or a final exam type problem, as opposed to just a homework or quiz problem. So do you guys have any questions about this example 3?
Yes.
Okay.
What was on the slide before?
Mhm.
No, I think no, before that too.
Okay.
I'm a bit confused why there's like 2 times 10 to the 12th power squared.
In F1 or F2?
F1.
F1. Okay, so we need to know the distance between this small star and the big orange star in order to calculate the force of gravity between them, right? Because if we look at this equation for the force of gravity, we have distance squared as the denominator. So we need to know that distance. We were not given that distance, though. We were given the other two sides of the triangle.
Oh,
Since we know those other two sides of the triangle, we're just using Pythagorean theorem to find that missing side.
but I don't, hold up.
Okay.
I don't really understand. Okay, but why adding though? I would understand if you did Pythagorean theorem like, oh, wait a minute. Oh, I'm thinking too hard about it. It's right there. And
I will just say confusion is a totally valid reaction to this right now, right? This might be the first time you're seeing this sort of thing. So if you feel confused and overwhelmed, that is totally valid for anybody that's watching this right now. But the more you see it, the more you'll get the hang of it. Anyway, so we are adding them together because the Pythagorean theorem is a squared plus b squared equals c squared, right? That's the version of Pythagorean theorem that we're kind of used to seeing. So a squared is just one side of the triangle squared, and b squared is the other side of the triangle squared, and c squared is the hypotenuse of the triangle squared. And it's that hypotenuse that is the distance that's missing that we're trying to find, right? So c squared in the Pythagorean theorem is actually r squared in our equation. So down here, I just plugged it in as a squared, this one side of the triangle, plus b squared, the other side of the triangle. And that equals c squared, which in this equation is r squared. So this denominator here, 2 times 10 to the 12 squared plus 2 times 10 to the 12 squared, this is just the Pythagorean theorem so that we can find that missing side of the triangle. Does that help at all?
Yes.
Okay, perfect. Any other questions about this example? Okay. So, bonus follow-up question for this example. Let's find the resulting acceleration of the small star. Right? So we know that there's a force of gravity on this star. That net force of gravity, or the total force of gravity that we just found, was 1.87 times 10 to the 26 newtons. From Newton's second law, we should remember that the net force equals mass times acceleration. So taking that equation and solving for acceleration, we get acceleration is net force divided by mass. So this is our total gravitational force that we just found, divided by the mass of that small star. That gives us an acceleration of 1.8 times 10 to the negative 4 meters per second squared. So again, since this question is now throwing in another topic, right? Newton's laws, this would be something seen on the test or a final exam. Okay. So I want to talk quickly about some other like related topics due to gravity and superposition of forces, and that's these Lagrange points. So Lagrange points, or L points, are points near two large bodies in orbit where a smaller body, a smaller object, can keep its position as stable or nearly stable. And so at these points, the gravitational forces from those bigger objects, let's say the sun and the earth, will kind of match up in a way that there would be some location where those two forces of gravity kind of balance out, and an object that's placed in that location will remain stable there, or nearly stable, right? So the gravitational forces of those bodies, the centripetal force of the orbital motion as the object goes around, sometimes the Coriolis acceleration, which you'll cover in rotational motion, they all match up to create these kind of equilibrium points. And now in any system, there are 5 points where we get nearly stable or completely stable points, these Lagrange points. So they will all be within the plane of orbit, right? So if we have the sun and the earth here, these Lagrange points will be in this same kind of plate, the same plane. But the locations will be different depending on different pairs of objects. So if you're considering the sun and the earth, the Lagrange points will be in a certain location. But if you're considering the earth and the moon, those Lagrange points will be in a different location for those two objects. So here is the sun and Earth. And as the Earth orbits around the sun, you can see these 5 Lagrange points are also moving around, respective to the Earth's motion around. So the first Lagrange point, or this point labeled 1, is between the sun and the Earth, right? Where the force of gravity from the Earth is balanced out by the force of gravity from the sun. The second Lagrange point is past the Earth. The third Lagrange point is exactly opposite the Earth in its orbit, so like behind the sun. And then Lagrange points 4 and 5 are at the same distance from each other, one in front of the Earth and one behind the Earth in its orbit. Okay, so we're not going to go through all of this math. It's just kind of if you're curious as to how we find these Lagrange points, here's how we can solve for them, right? Based on what we know about gravity. And if we have the case where mass 1 is much larger than mass 2, like we would for the sun and the Earth, we get this sort of result. Okay, the radius of that Lagrange point is the radius of the Earth's orbit cubed times the square root of mass 2, which is the Earth, divided by 3 times the mass of the sun. Okay, we'd follow a similar logic for the second Lagrange point, except you'll notice this slight difference here is a minus because it's in front of the Earth, and here it's a plus because it's behind the Earth. And the others are even more complicated to solve for than that. So these would not be something, I don't think these would be something that you solve for in physics 1. I think I solved these in orbital mechanics and spaceflight mechanics, not in physics 1. But I just wanted you to see them because they're interesting. So several planets have what are called Trojan satellites in their L4 and L5 points, which are basically kind of like asteroids that they just propel around in their orbit, that maintain that constant, that stable distance from the planet as they go around. So for example, Jupiter has more than 1 million of these Trojan satellites in its L4 and L5 points. So they're just like 1 million random objects kind of orbiting around with Jupiter in its same orbit, purely because of these forces matching up to create these stable zones. And so we have placed satellites at some of these locations in the Earth-Sun system, and in the Earth-Moon system. So for example, the James Webb Space Telescope, which has been in the news lately, I'm super excited about that. But this James Webb Space Telescope was placed at the L2 point behind the moon. And so it just needs a little bit of correction every now and then to kind of maintain that position in the L2 point. Because the L2 point is not completely stable, it's a nearly stable point. So it just kind of hovers there in that L2 position, and then we can kind of just like minorly correct it every now and then when we need to keep it in that point. I know, yeah. So comment in the chat. It's unfortunate a mirror was struck by a micrometeor. Yeah, absolutely. Super unfortunate that that happened, but not uncalled for, because if you think about it, right, like we had just talked about how there are potentially millions of these objects that just kind of cluster in these Lagrange points because they're stable. So the fact that we're putting this space telescope intentionally in one of these Lagrange points was for the sake of, cost effectiveness for the James Webb Space Telescope, but also that it does come into risk because there are other things that hang out there in these Lagrange points, such as micrometeors. So it's, you got to weigh the benefits and the risks there. Okay. So gravitational potential energy, we just have a few minutes left. We're not going to get through all this information today, and that's all right. I'll put all of these notes on Canvas for you later on so you can go through them at your own speed. But we need to talk about gravitational potential energy because now it is a little bit different now that we're thinking about in space. So previously, our gravitational potential energy, we calculated using mgh or mgy. Remember that mass times the acceleration due to gravity times whatever height we were above our reference point. So that's great if we're near the surface of the planet and acceleration due to gravity is constant. But if we're not near the surface, then little g is not constant, right? We did some example problems yesterday, the International Space Station. We saw that even at a height of 405 kilometers above the surface, our acceleration due to gravity changed to like 8 point something. So as we go away from the surface of the Earth, that acceleration due to gravity changes, which means our gravitational potential energy is changing as well. So this is our new equation for gravitational potential energy. Negative big G times mass 1 times mass 2 divided by R. And you'll notice it's very similar to the force of gravity equation, which was G m1 m2 over R squared. So make note of this equation. It's an important one you'll keep coming back to. Gravitational potential energy in space is now negative because it's attractive. G m1 m2 over R. Okay. So notice there is a negative and there is not a squared. And so really the changes in the gravitational potential energy are more important than a particular value itself. So let's think through this equation really quickly. Where would the potential energy, the gravitational potential energy, be 0? Okay. Well, at infinity is the only place where the potential energy due to gravity is 0, right? Because our masses are never going to go away. It's not like we're just going to randomly lose the sun. Like it won't just blip out of existence. Okay, so the masses aren't disappearing. And the only other way we can make this value 0 is to make R, that distance away from the object, equal to infinity. So as we get closer to an object, so coming in towards the Earth, does the gravitational potential energy increase or decrease? It decreases. It gets more and more negative. So as that radius changes, our gravitational potential energy will change inversely. But we have that negative sign that we have to consider, which changes things. Okay. I want to go through this one last example. If you guys have to head out at any point, you're welcome to. I know it's 4:28. But I want to go through one example problem of this new gravitational potential energy before I wrap up with you guys. Okay, so Spaceballs is our example 4. So if we ignore orbital effects and we just drop a ball from the International Space Station, which is 405 kilometers overhead, how fast is it going when it hits the ground? So we're going to try this 2 different ways. First, using our old equation for gravitational potential energy, and now using our new equation. There's a negative sign missing in there. Sorry about that typo. Okay. So some numbers that we need to know. The radius of the Earth here is 6,371 kilometers. And the mass of the Earth is 5.97 times 10 to the 24 kilograms. So here's a picture of what is happening, right? Here's the International Space Station. We're dropping a ball, plummeting down towards the Earth. The International Space Station is 405 kilometers above the surface. So here's the old way, the way that we had been doing it, which should seem familiar to us. the change in energy due to outside or other forces is 0. So we're not considering friction, we're not considering air resistance. Energy is conserved, so our initial energy equals our final energy. Initially, this ball has all gravitational potential energy, right? We're dropping the ball, we're not throwing it. So its initial speed is 0, which means its initial kinetic energy is 0. And when the ball hits the ground, when it hits the surface, its potential energy is 0, and it has all kinetic energy because it's moving very fast at that point. So that means the mass, and I'm putting M2 because we're talking about the mass of the ball, not the mass of the Earth. So the mass of the ball times G times H is 1/2 times the mass of the ball times that final speed squared. So once we go through that same sort of algebra that we'd been doing in energy, right, we'll see those masses will cancel each other out. G is 9.8, H is 405 kilometers. We need that in meters. We get a final speed of 2,817 meters per second. Okay, so this would be following that same pattern that we had seen, what was that, last week with energy? We would end up with this final speed. Here's our new way of doing it, okay, using our new equation. Same initial concept of conservation of energy, right? We're still not considering friction or air resistance. So our initial energy is still equal to our final energy. But now, since our distance is measured from the center of the Earth as opposed to the surface of the Earth, that means we have an initial gravitational potential energy because it's above the center of the Earth. And we also have a final gravitational potential energy because even though it's at the surface of the Earth, it is not at the center of the Earth. So it still has a final gravitational potential energy there. Okay. So here, I actually put in the negative signs. Our initial gravitational potential energy is negative G times M1 times M2 divided by the radius that the International Space Station is at. And that equals our kinetic energy of the ball plus our gravitational potential energy. But since there's a negative sign in that equation, it's a minus here. And the final radius that it's at is the radius of the Earth. Okay. So the radius of this International Space Station is not just the height above the surface, because remember, these distances are measured from the center of the Earth. So we have to have the altitude of the International Space Station plus the radius of the Earth. And since those values are in kilometers, I'm multiplying by 1,000 to get it to meters. So once we plug in our values, right, the radius of the International Space Station is this number. The radius of the Earth, here, we put that in meters. Mass of the Earth would go in from M1. Mass of the ball is in each term, so that would, you can cancel those out. And so once we go through our algebra magic, we get a final velocity of 2,733 meters per second. So you'll see that there is a difference between the value for the old way and the value for the new way. They're only about 3% off from each other. So the old way is not as accurate as this method, but it's still a good approximation for things that are still fairly close to the surface of the Earth. And it's also a good way to check your math because this equation is a little bit more complicated looking than the previous one for the old way. So if you want to know if your answer is kind of in the right ballpark, then feel free to double check your answer using the old way. So you can use the old way if you're within the Earth's atmosphere, it will give you a pretty good approximation. If you're farther away than the Earth's atmosphere, then it's probably better to use this new equation for gravitational potential energy. Okay. So do you guys have any questions about example 4 or anything that we've talked about today? Okay, so unfortunately, I didn't get a chance to go through this whole PowerPoint with you. There's still quite a bit that I didn't have a chance to cover. But I'll put all of my notes on Canvas for you, all of the full PowerPoints. I'll put the full PowerPoint for rotational motion as well, even though we didn't cover that one. Yeah, all of my notes, all of my resources will be there for you on Canvas for the next few days. So definitely check them out, download them if they're helpful to you. If you have questions about anything, now as you go through my materials or later on when you take Physics 1, please feel free to reach out to me. I would love to help you as best I can. You have my email. So yeah, reach out to me. If you see me around campus, feel free to stop and say hello. But I've had a great time teaching you guys, and I've appreciated how much you participated. So thank you for hanging in there with me, guys. And it's been a pleasure to teach you. And I wish you the best of luck as you take Physics 1 and all of your other classes at FIT. So have a great day, a great weekend, a great rest of your summer. Please remember to do that post test, and please reach out if you have any questions. Otherwise, have a great one. Bye.
Thank you very much. Have a wonderful summer.